So here is our first illustration. And so we are looking at an illustration in R2, or in 2 dimensions. We're going to have 2 equations and 2 unknowns. So I want you to start by considering this beautiful following linear system. So we have our first equation is 2x sub 1 minus x sub 2 equals 0. And equation number 2 is minus x sub 1 plus 2x sub 2 equals 3. So the first thing that we want to do is take this linear system and break it down. So I want to break it down into those 3 equivalent formats. We've got the matrix equation, the vector equation, and the augmented matrix. So here we go. Let's start with the matrix equation. So we now know that the matrix equation has the form matrix A times vector x equals vector B. So looking up at our linear system, again, we know we're in R2. We want the coefficient matrix, so our matrix A. Looking at the coefficients of our variables, our first column is 2, negative 1. The second column is minus 1, 2. And now this is multiplied by that vector x in R2. So we have 2 entries, x sub 1, x sub 2. And this is equal to the constant vector, that vector b. So that's defined as 0, 3. Beautiful. Now let's go ahead and let's take this and break it down to the equivalent vector equation. So this is the linear combination of the columns of matrix A. So we can even write this as a linear combination. If we look back up at the matrix equation, we have 2 columns. There's column vector A sub 1 and column vector A sub 2. So the vector equation will have the form x sub 1 times column vector A sub 1 plus x sub 2 multiplied by the column vector A sub 2, and that's equal to the constant vector b. So let's break this down. So we have our first scalar or weight or coefficient, x sub 1, multiplied by the first column of the matrix, 2, negative 1, plus that second scalar, x sub 2, multiplied by the second column vector of matrix A, negative 1, 2. And that's equal to that constant vector 0, 3. Beautiful. And last but not least, we also want to go ahead and break this linear system down to the equivalent augmented matrix. So again, the augmented matrix is the format that we typically use when solving. And let's just think about how this would be denoted real quick. Again, we have the 2 columns of matrix A, vector A sub 1, vector A sub 2. There's your coefficient matrix. And we're augmenting this bad boy with vector B, our constant vector. And we use this to solve for the unknown vector x. So here we go. Our augmented matrix for this system has the first column 2, negative 1. Our second column is negative 1, 2. Again, there's your coefficient matrix. And we augment this with vector b, 0, 3. So there you have it. Technically we have 4 different formats here for the same system. We have the system of linear equations that we were given. We now have the matrix equation for this system. We have the vector equation for this system. And we have the augmented matrix for this system. They're all representing the same system. So now that we've looked at these different formats, we want to think about the geometric interpretations of this system of linear equations. We're going to have 2 different interpretations based on, are we looking across the rows or are we looking down the columns? So I want to go ahead and look at this now in some detail with you. So get excited. Here we go. So here we are about to consider the row picture of our system in R2. So when I say row picture, I literally want you to look across the rows, 1 row at a time. So to see the row picture geometrically or graphically, all that we need to do is graph the given system in R2, 1 row at a time. So in other words, to see the row picture, we simply need to sketch the line that represents the equation in each row. So here we go. row number 1. So the way that row 1, again, looking right across that first row, we see we are given the linear equation 2 times x sub 1 minus x sub 2 is equal to 0. And what I want you to do is keep in mind that x sub 1 represents x and that x sub 2 represents y. So we can think of this in the equivalent form, 2x minus y is equal to 0. And now considering we want to look at the geometric interpretation, let's take this line one step further and rewrite it in the graphing-friendly format, y is equal to 2x. So there is our first row. And now we want to do the same thing with our second row, R2. So again, looking back up at your system and looking right across that row, we are given minus x sub 1 plus 2x sub 2 is equal to 3. So rewriting this in a more friendly format, we can say that this is minus x plus 2y is equal to 3. And again, taking that one step further and rewriting this in that graphing-friendly format, or solving for y, we are left here with y is equal to minus 1/2 x plus 3/2. And there you have it. So we have looked across the rows of our linear system, and we see we are given 2 linear equations, or 2 lines in R2. So let's go ahead and sketch these now, because the row picture is going to help us to see, hopefully, the point that satisfies both of these lines. So let's start with row number 1, or line number 1. So looking at this line, we have a x and y intercept at the origin. And let's find a couple of other points on this line. We know that when x is 1, y will be 2. And when x is negative 1, y is negative 2. So if you have graphing paper, I encourage you to use it here. Otherwise, label and try your best. So here we go. Here is the graph of our first row. This is R1, originally given to us as 2x sub 1 minus x sub 2 is equal to 0. Now what about the second row? So the second row is this diagonal line. So let's see, we have a y-intercept at 3/2, or 1.5, so right about here. And we have an x-intercept at -3. And we could sketch it at this point, but let's see if we can take this one step further. What about when x is 1? What is y? It's 2! Woohoo! So hey, oops, we did it. We found a point that satisfies both lines. So again, if you have that graphing paper, it'll be most helpful here. Otherwise, labeling is sufficient. So here is our second row, r sub 2, originally defined as minus x sub 1 plus 2x sub 2 is equal to 3. And notice here, looking at our beautiful row picture, our geometric interpretation of the rows, we can see the point that satisfies both lines at the ordered pair 1, 2. So this is the solution to our system. We can conclude that therefore the point that satisfies both lines, or both rows, so satisfies both lines or both rows, is that ordered pair xy defined as 1, 2. Now, again, typically we're going to write this in our vector form. So the solution vector is equivalent to this point that satisfies both lines. The solution to our system, vector x, with the entries x sub 1, x sub 2, is defined by the column vector 1, 2. And there you have it. So our row picture is our familiar intersection of 2 lines in R2. And here comes the exciting one. We have to consider the column picture. So when we're considering the column picture, we want to think about the system in terms of the vector equation. So real quick, we know our vector equation is x sub 1 multiplied by the column vector 2, negative 1 plus x sub 2 multiplied by the column vector negative 1, 2. And this is equal to the constant vector 0, 3. Again, this is our vector equation. So as we begin, I want you to note that the column picture is asking us to find the correct combination of the columns of the matrix to produce vector B. So what is this saying? Well, this is saying we need to write vector B as a linear combination of the column vectors, vector A sub 1 and vector A sub 2. So in other words, we are looking for the x sub 1 multiplied by the column vector A sub 1 plus some x sub 2 multiplied by the column vector A sub 2, that's going to produce vector B. And the part that we're looking for, that correct combination, is how many of vector A sub 1 and how many of vector A sub 2 are going to equal vector B. Now, we actually already know how many of each column vector that we need. If we think back to the row picture, so we say that from the row picture, we already know that vector x with the entries x sub 1, x sub 2 is equal to 1, 2. So this solution, right, that intersection point is telling us that we're going to need 1 of the first column plus 2 of the second column to produce that constant vector B. So let's think about this graphically. This, I think, is the most fun part. So to get us started with our geometric interpretation, you just want to sketch the two column vectors. We want to sketch column vector A sub 1 and column vector A sub 2. So see, column vector A sub 1 is defined by the components 2, negative 1. So here's the point 2, negative 1. So from the origin, here is our first column vector. That's column vector A sub 1, again defined by the components 2, negative 1. And column vector A sub 2 is defined by the components negative 1, 2. So there's that point negative 1, 2, and here is the column vector. That's column vector A sub 2, defined by the components negative 1, positive 2. So how are we going to produce vector B using these? So a little vector arithmetic. We are going to take, again, 1 of column vector A sub 1, and we're going to add 2 of column vector A sub 2 to it to produce vector B. So here we go. Starting from the origin, we need 1 of column vector A sub 1. So here is 1 times column vector A sub 1. And now from this terminal point, we're going to now add the scalar multiple 2 times vector A sub 2. So keep the components of vector A sub 2 in mind here. So again, from this terminal point, we're going to add 2 of vector A sub 2. So we need to move up 2 units and then to the left 1 unit. So here is 1 of vector A sub 2. But again, we need 2 of them. So again, we're going to move up 2 units and to the left 1 unit. So here is that full scalar multiple 2 times vector A sub 2. And look at the point we landed at. What is this position vector? This position vector is 0, 3. It's vector B. Woohoo! So we can see how if we add 1 of column vector A sub 1 and add 2 of column vector A sub 2, we're able to produce that vector B. This is the correct linear combination of those two column vectors that produce our constant vector. So this concludes our geometric interpretation of our column picture in R2.